In this video, we are going to talk about what is zero-point energy and its significance. So before starting this video, please like this video, and subscribe to our channel for the future updates. Let's start. Zero-point energy. A quantum mechanical system's zero-point energy, ZPE, is the lowest possible energy. The Heisenberg uncertainty theory describes how quantum systems, unlike classical mechanics, continuously fluctuate in their lowest energy state. The empty space of the vacuum, including atoms and molecules, has these properties. The universe, according to quantum field theory, is made up of continuous fluctuating fields, matter fields, whose quanta are fermions, i.e., leptons and quarks, and force fields, whose quanta are bosons, e.g., photons and gluons. There is zero-point energy in both of these fields. Since certain devices can sense the presence of this force, these fluctuating zero-point fields contribute to a reintroduction of an aether in physics. However, this aether cannot be thought of as a physical medium if it is to be Lorentz invariant and not contradict Einstein's theory of special relativity. Scientists wanted to find the smallest amount of energy possible in a given region of space, so they created a vacuum by removing all things, air molecules, and particles with kinetic energy. They discovered there was still energy in this field of space after they did this. It is electromagnetic infrared radiation, which is similar to light but has lower frequencies, that is responsible for transporting heat from the sun to the Earth. To get rid of all infrared radiation, they lowered the temperature of the region of space to -273 degrees absolute zero and turned it pitch black. Then they realized there was still energy in this region of space, which they dubbed zero-point energy. By causing friction in the electromagnetic universe, energy causes the speed of light to be limited. It is also the energy that allows for the existence of atoms. Have you ever heard of electrons orbiting around specific energy stages, or orbitals? As an electron accelerates, for example, orbiting around a proton, it emits energy in the form of electromagnetic radiation, and its horizontal velocity slows, allowing it to fall through the object. Have you ever wondered why these energy levels occur, which enable electrons to orbit without losing energy and colliding with the object? The energy consumed by electrons from zero-point energy equals the electromagnetic radiation given out at these energy levels, according to one hypothesis, which explains why the electron does not lose spinning velocity and fall through the object. As a result, atoms will exist. Physics currently lacks a complete theoretical model for understanding zero-point energy, and the disparity between theorized and observed vacuum energy is a major source of debate. The zero-point radiation of the vacuum, according to physicists Richard Feynman and John Wheeler, is an order of magnitude greater than nuclear energy, with a single light bulb holding enough energy to boil all of the world's oceans. However, any such energy would gravitate, according to Einstein's theory of general relativity, and scientific evidence from the expansion of the universe, dark energy, and the Casimir effect suggests that any such energy would be extremely small. The fermion field has a negative zero-point energy, while the boson field has a positive zero-point energy, and thus these energies cancel each other out, according to a popular proposal. This would be valid if supersymmetry were an exact symmetry in nature, but the LHC at CERN has found no evidence to support it so far. Furthermore, if supersymmetry is real at all, it is understood to be a broken symmetry that is only true at very high energies, and no one has been able to demonstrate a theory in which zero-point cancellations occur in the low-energy universe we observe today. This disparity is known as the cosmological constant problem, and it is one of physics's greatest unsolved mysteries. The vacuum holds the secret to a complete understanding of existence, many physicists claim. Significance. Ground state energy should be taught instead of zero-point energy. Any system's ground state is its lowest energy state, which by definition prevents it from transitioning to a lower energy state. As a result, in a device in ground state, no energy is available. Although the energy that remains in the system in its ground state could be referred to as zero, formulas representing energy of states assign a non-zero energy to the ground state, which is referred to as zero-point energy. This value is greater than zero, but it's best to call it zero because a device in its ground state can't take any more energy. Zero-point energy is incredible in every way. This seems to hold physicists in a state of disbelief, as they are unable to comprehend its meaning. There's the issue of whether the ZPF is conservative, for example. Unlike politics, conservative physics fields preserve energy and therefore follow the first law of thermodynamics. According to Dr. Robert Forward, if ZPE is not restrictive, we can obtain an infinite amount of energy from the vacuum. We can still extract energy from the ZPF if it is proven that it is a conservative field. It's just that we'd have to bring energy in and store it in some way in order to get it out. So far, the evidence seems to support a non-conservative ZPF, with debates raging on both sides. Dr. Forward has also convincingly shown the capability of ZPF storage and retrieval. Professor Jordan McClay won a NASA grant to try to extract ZPE from elongated, oscillating, tiny metal boxes, and an article titled, "Energy Unlimited," appeared a few years ago. However, vacuum fluctuations remain a matter of controversy, mostly because their energy is infinite, according to a physics journal paper. More notably, their energy per unit volume is limitless. Surprisingly, this seems to cause intellectual disabilities that can only be overcome artificially. Problems with the infinite energy of vacuum fluctuations have contributed to the belief that vacuum energy could be forced to vanish by definition, due to the need to regularize the infinite energy momentum tensor. This, however, adds to the complications. This process produces ambiguities and inconsistencies, which contribute to a breakdown of the energy momentum tensor's normal symmetry properties at the quantum level. What do you think of our video? Let me know in the comment section below. If you enjoy this video and want to hear from me again, be sure to hit that subscribe button before you go. Thanks for watching.